All right, chapter 12, section 5, number 15. Use mathematical induction to show that the given statement is true. N squared plus n is divisible by 2 for all natural numbers n. Okay, so divisible by 2, that's all the even numbers. So let's count that out, right? Divisible by 2. Divisible by 2, it means all the even numbers, right? So if we point them out, that's the number 2, the number 4, the number 6, the number 8, the number 10, number 12, dot, 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 right? And so what do they all have in common? They're multiples of 2, they're divisible by 2, and it also means that they can be rewritten as in the following way. They can be rewritten as 2 times 1, that first one, comma, and then 2 times 2 can be that second one, and then 2 times 3 is that third one, and then 2 times 4 is that one over there. So we can always rewrite any one of those numbers as 2 times a number, and notice that it could be 2 times 1, 2 times 2, 2 times 3, 2 times 4. So we can rewrite it as 2 times n, where n equals 1, 2, 3, 4, dot, 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 dot. So 2n, where n equals any one of these positive integers, or the counting numbers, represents even numbers. Good? Okay, so that's important to understand what it means by it's divisible by 2 for all natural numbers n, right? So this is where n equals natural numbers. Okay, so let's explore this thing. N squared plus n is divisible by 2 for all natural numbers n. So let's just check this out for ourselves and make sure it works. So let's say if n equals 1, then we're saying that 1 squared plus 1 is divisible by 2. Is divisible by 2. Okay, does it make sense? Yeah, that's going to be 2, right? And 2 is divisible by 2. So it's true. It's true for that first one. Okay, let's check another one. If n equals to 2, then we end up with 2 squared plus 2, and then is divisible by 2. Is divisible by 2. Good, okay, well that's going to be 4 plus 2, that's going to be 6, and 6 is divisible by 2. Also true. So far, it looks like it's working out. It worked for n equals to 1, and it worked for n equals to 2. Let's just jump to some random larger value, just to confirm. We're just trying to make sense of this whole thing. So let's say if n equals, I don't know, about 12. Is it going to work if n equals to 12? Well, maybe because it's even, maybe people are more convinced that it might work. Let's try about 11. Does it work for 11? Okay, so then we end up with 11 squared plus 11 is divisible by 2. Good. So that's 121 plus 11. That's going to give us 132. Yeah, and 132 is divisible by 2. Good. So it worked for 1, it worked for 2, worked for 11. Okay, so we're mildly convinced that maybe this is true, but we now need to do a formal proof by induction. Good. So we're ready to prove it by induction. So proof. Okay, step 1 in the official formal proof is to do it for the case of n equals to 1, which we already did over there, but now I'm just going to rewrite it so that we can have the nice formal proof. Proof, step 1, show it works for the first case, n equals to 1. Okay, so we have n squared plus n is divisible by 2, which means that for us we'll end up with 1 squared plus 1 is divisible by 2, and then that must mean that 1 plus 1, which is 2, this is 2, is divisible by 2. Okay, so step 1 worked out. Step 2 is to assume that it works for some larger value n, right? Assume it works for n equals to k. I'm going to put k in, put it in green. N equals to k, some large value in the system, right? Because n is supposed to be a natural number. So n is equal to 1 or 2 or 3, ... Some k value is out there. And then the one right next to it is going to be k plus 1, and then k plus 2, and so on and so forth, right? It's one of those numbers. We've already shown it works for 1 and 2. We showed it works for 11. We're just assuming k, some number way down the road there. And we're going to be working with these two. So we assume this one's true. It works for that one, which means that this part is assumed to be true, that when we take that kth number and we square it, and then we add k to it, that this is a number divisible by 2. This is divisible by 2. Good. Okay, what does it mean to be divisible by 2? Well, it means that k squared plus k is an even number. K squared plus k is an even number, right? So divisible by 2 means it's an even number. It also means that I can make it equal to 2 times some value, some counting number. K squared plus k is then equal to 2 times some number. Now, I don't know what that number is, right? It's some value. I know it's a counting number, but it's not necessarily k, right? It's just some number out there because it's even, right? This turns out to be an even answer. So like, let's say, for example, up here, when I was working with n equals to 11, it turned out that the whole thing added up to 132. So what is that, 37, 36? Why am I having a brain fart here? That's going to be 65 leads you to 160, leads you to 120, and 66. Yeah, 2 times 66 should lead you to this number, right? So 132 equals to 2 times 66. Good. So because it's even, it means that it can be written as 2 times a number. Now that number is not the same as this value here, the initial value that you substituted into your formula. It's just some other number. And it might be an even number, it might not. It doesn't, that's not part of it. It's just that it's 2 times some value, right? That's what it means for it to be even. So I can choose some value here. I don't know. How about a? I don't know. Let's say a, where a is also a natural number. Natural. Right? It's some counting number. A equals either 1 or 2 or 3 or 4 or 5 or ... Good. Okay, so all these things mean the same thing. Just saying that k squared plus k, whatever value that is, saying that it's divisible by 2, is the same thing as saying, oh, okay, it's an even number. k squared plus k, it's an even number. Also, k squared plus k equals to 2 times a, right? Because it's even. So I know that 2 can be factored out of it, and it can be rewritten as 2 times a, where a is some natural number. Good, good, good. Okay, now here's the hard part, and the reason I represented this in 3 different ways is because I have no idea which one is going to be useful for me. So let's go over here and start playing around with it. Now we need to assume things, we need to prove, we need to show. Step 3, show it works for n equals to k plus 1, the one right next to it, k plus 1. Good. So in other words, we need to show that when we plug in k plus 1 into our little formula, remember we had a formula of n squared plus n, then this is going to be equal to blank squared plus blank, where that blank is the k plus 1. Go away. K plus 1 and k plus 1, right? Our mission is to show that this must be divisible by 2. Okay, show that this must show that this is divisible by 2. Is divisible. Must show this is divisible by 2. Okay, so let me factor out the k plus 1 and see if that's helpful. If I factor out the k plus 1, we get k plus 1 factored, and then we end up with a k plus 1 plus 1, which means we end up with k plus 1 plus 1 times k plus 2. And up here we end up with a k times k plus 1. Okay. How about if I FOIL it then? Let's say if I FOILed it, I end up with k squared plus 2k plus k plus 2. Good. Okay. So if I'm going to reorganize these and say that this is k squared plus k plus 2k plus 2. And I know I could combine those, but I'm going to leave them alone because now I notice that I end up with k squared plus k. Hang on 1 second. Okay. Okay. K squared plus k plus 2k plus 2. Okay, so this is exactly what we assumed in step 2. K squared plus k is even, right? K squared plus k is divisible by 2. K squared plus k is an even number. K squared plus k can be made equal to 2 times some number, right? That's what it means for it to be even. And it's that third one that I'm going to take advantage of. By our assumption, it means that this is equal to 2 times some number. I don't know what that some number is, but it's definitely 2 times some number. Good. And then I can drop down the 2k and the 2. And now I can factor out a 2. They all have 2's. 2, 2, 2, 2, 2. So if I factor out all those 2's, I end up with 2 times a plus k plus 1. Good. And that's all that really matters, because I know that a is some natural number, I know that k is some natural number, and I know that if we add 2 natural numbers and we add them, we get another natural number, right? And then we add 1 to that, it's still a natural number. Right, so I'll put that logic in here. Let, I don't know, W equal A plus K plus 1. So because A equals some counting number, come on, number, and K equals some counting number, then W equals some counting number. Good. So I can rewrite all of this as 2 times W, where W is just this whole thing over here, and W equals some number, some counting number. Otherwise known as a natural. The natural numbers are the counting numbers. Okay, so then we've shown that the original thing we wanted to do is true. Let's zoom out a little bit. Right, so then we've shown that this is divisible by 2 because it can be expressed as 2 times some counting number. Right, so this was equal to this. I should have put equal signs, which equals that, which equals that, which equals that. And then by the induction assumption, by step number 2, using step number 2, right in there, we were to say that this is 2 times some natural number, right? We can put that in here, where A equals a natural. Good. And that equals this. So therefore, this whole thing, A plus K plus 1, must be some natural number, counting number. So we have that. Okay, so if we group these things together, all of this is saying exactly what we wanted, that K plus 1 squared plus K plus 1 is equal to 2 times W, where W equals a natural number. Come on. So K plus 1 squared plus K plus 1 is divisible by 2. Is divisible by 2. Good. Okay, so because we've shown, I'm just kind of walking through the whole proof one more time. Back up here, the original statement was to show that. Oh, I can't really read that, can you? The original statement was to show that n squared plus n is divisible by 2 for all natural numbers n. So we first show that it works for n equals to 1. N squared plus n is divisible by 2. That one worked for 2. Then we assume it's true for n equals to k, where k is some natural number, right? Where k is some natural counting number. And so we just assume it's true. And saying that it's divisible by 2 is the same thing as saying that it's an even number. And saying that it's equal to some even number means that it's equal to 2 times a, where a is some other counting number, right? In other words, we can factor a 2 out of this. That's really what it's saying. It's even, therefore it's divisible by 2, therefore 2 can be factored out of it. It can be rewritten as 2 times something. Next, we need to show that it's going to work for n equals to k plus 1. So we plug in a k plus 1, we get this. This is what we're trying to show. If I FOIL this out, I factored out the k plus 1 first and then FOILed it out. And then we end up with this expression. This first part, I just reorganized it after factoring it. It's equal to 2a, right? Where a is some counting number. That's by our assumption in step 2. And now we can conclude that the statement of k plus 1 squared plus k plus 1 is equal to 2w, where w is some natural number. Therefore, k plus 1 squared plus k plus 1 is divisible by 2. And so by the induction, proof by induction, we've shown that it works, that the original statement is true. N squared plus 1, I'm sorry, n squared plus n is divisible by 2. Right, so we can conclude that, n squared plus n is divisible by 2. For all natural numbers n. For all natural numbers n. And we're done. Okay, any questions? No?
Thank you.
You're welcome. So no questions from anyone?
Actually, well, I just had a question on another problem on the homework.
Oh, okay. So no questions on this one from anyone? No, before we move on? No, no, no? Okay, let me get another page going here. What's the question?
13.1, number 13.
13.1, number 13. All right, let's see what. Do I have that? Okay, 13.1, number 13. 13. This one right here. Estimate the limits naturally and graphically using the table of values. Estimate the values. This one?
Yes, please.
Okay, so let's zoom in here. If I can get a. Well, very little work needs to be shown for something like this, right? It says use a table of values to estimate this. So we just have to use our calculators to solve this as best we can. And what we want to do is create a table using our calculators, right? That's why it's got the little calculator, little symbol on there. So something like this, what you would create is your own table, kind of like these tables up here, except that here they were kind of leading you in that direction by, providing you this little table. Whereas in these problems, it's a little more up to you to create the table and choose the values that you would like to put on there. So let's use our calculators to solve it.
Okay, all right. Thank you, though, because I may have overlooked that part where you needed to use the calculator and I just try to solve it by hand.
Oh, okay. Right. So this process is a very useful process in the beginning to try and get a good sense of what's happening with this function. So so I think you'll have a few of these in the beginning. All right, so let's make sure we type this in the right way, and that's probably the hardest part of this question. You have to type in 5 to the power of x, space, and then minus 3 to the power of x, and then space, and then parentheses divided by x. Okay, so make sure that if you don't have, if you have one of the older calculators, it doesn't really do this thing with a little space like that. It does a little caret symbol. So just make sure that you wrap all the appropriate parentheses to make sure that you have the correct statement. Okay, so then this creates our function. If we go over to table set, it should be under ask and auto. Okay, And then if we go over to table, second table, here is a place where if we insert values, it'll calculate it for us. So this means that if we take 5 to the power of 2, that's going to be 25. 25 minus 9, that's going to be 16. 16 divided by 2 is 8. Right? So if I replace all these x values by a 2, I will get an 8. And this calculates it for us quickly. Okay, so let's get rid of those. And okay, I'll leave the 2 there. Now, what happens if we plug in a 1? Okay, that's going to be 1 there, 1 there, 1 there. That's going to be 5 minus 3, that's 2. 2 over 1, that's going to be 2. Good, so hopefully that's true. If I put a 1 there, I get a 2. Okay, so this automatically calculates that quickly for us. And what we're interested in knowing is what happens as we get close to 0, right? Very importantly, though, never actually 0. Because if we plug in 0, we know we're going to get an undefined, right? We'll end up with 5 to the 0 power, that's just 1, minus 3 to the 0 power, that's just 1. So we'll end up with 1 minus 1, that's 0. 0 in the numerator, 0 in the denominator, that's undefined, right? So we can't just plug in a 0. However, we want to know what happens when you get close to 0, right? This limit thing, this is describing the process of approaching what happens to the what happens to this function as x approaches 0 from either direction. So let's approach it. From the positive direction, I can go to 0.5, then I can go to 0.4, then I can go to 0.3, then I can go to 0.2, then I can go to 0.1. Okay, we see that it's getting a little smaller, maybe getting close to 0.5, maybe. Let's get really close, 0.01. Okay, let's get really close. Okay, that's really close, and it seems to maybe kind of settling in to 0.51, right? So as you can see, this process is not perfect because I don't know if it's just that it's approaching 0.51 or maybe that I haven't gotten close enough. Maybe if I get closer, maybe I'll approach 0.50, right? Maybe. And we are a little limited because our technology here, our calculators, is not going to let us get too close. Eventually, it'll just do some rounding on its own, and then we'll be off by a little bit. But it seems to be settling around 0.51 from the positive direction. So far, all these numbers have been approaching 0 from the right side of the number line. Now let's approach it from the left side of the number line, which in this case happens to be all negatives. Okay, so then if we approach it from the other direction, I'd end up with negative 0.5, for example, and then negative 0.4, and then negative 0.3, negative 0.2, negative point. Oh, I hate this thing that doesn't. It starts erasing all of them instead of letting me scroll down to more values. It's really annoying. But okay, so let's go in this direction. Negative 0.5, negative 0.4, negative 0.3, negative 0.2, negative 0.1, negative 0.01, okay, negative 0.001. Yeah, so it looks like from either direction, we get really close to about 0.51. So that's going to be my guess. 0.0001. Yeah, so from either direction, it looks like it's really getting close to something in the neighborhood of 0.51. Good so far. Okay, so we have a table. So this just says create a table. This exercise says use a table of values to estimate the value of the limit. This isn't a proof. This isn't confirmation. We could still be wrong, and it's not an exact answer, right? I'm just going to round to 2 decimal places and say that it's about 0.51. It's a good approximation. It's a good guess. In many situations, a good guess is good enough. When you get out in the industry, you'll find that we do estimations all the time. And sometimes 2 decimal places is good enough, and being fairly confident that that's the answer is good enough. In some cases, it's not good enough. Sometimes you need to be totally confident that that's the answer out to 20 decimal places. So you might have to do a lot more work to get a very good approximation, right? If you're in industry and you're making a guess about, I don't know, how many Doritos to produce that day so that it meets some sort of, standard or something, and if you get it wrong, oh well, you made too many Doritos that day, and you just wait till the next day and repackage whatever's left over. I don't know. It might not be a super crucial decision, so you do a rough estimate and you're happy with that. On the other hand, if you're making telemetry approximations for landing a probe on Mars, you only get one shot at it, and if you make a mistake, the thing explodes on entry, and a $5 billion project disappears. In a case like that, you want to be really confident and very accurate to a lot of decimal places. So you just gotta kind of take it in stride and depends on the context. But for this context, a couple of decimal places is fine, and we're pretty happy that it's about 0.51. We can also use the graph part of it to get a good estimation. So if we graph this, so I want to get close to 0. So let's look at my window. Let's make x go from -1 to +1. So I want to get close to 0. That should capture the domain. And the outputs look to be close to 0.51. So let's make it from 0 to 1. That looks pretty good. That should capture the part of the graph I want. There it goes. So I want to know right here, what happens as you get close to 0 in either direction. So I can hit the trace button to give myself a pretty good approximation. Right? And again, this is just an approximation. See how as I get closer and closer, this little blinking X indicates that the input value is here on the x-axis, and that it's heading closer and closer to 0 from the right end, from the right side of 0. Good, and it's getting really close to that value, and then it's undefined right at 0. And then from the other direction, if I go towards 0 in this direction, it's getting really close to it. Right? If I want to get an even better approximation, I can zoom in, and I don't know, maybe it's 0.50 that equals the answer, right? I can hit zoom. Let's go right in there and hit zoom in, the second option. Zoom in. I get an even better approximation. Oh wait, it lost its trace. There we go. Okay, so then we get an even better approximation after we zoom in. Right, one little tick to the next side of it. Looks like it's a little past the 50, 0.50. And on the other side, yeah, it's really close to 0.51. So it looks like 0.51 is a pretty good guesstimate for it. Okay. Any questions on this one? That's all you're supposed to do with this. It's just a good way of getting a good estimation for what the limit is. But this is not a proof that that's the limit. So we'd have to do more work. So the work you attempted to do it by hand, that's what you would do to show the exact answer and be confident about the exact answer. However, at this point, that's kind of hard because we haven't learned any rules about what to do when the variable is in the exponent. In the next section, we learn some rules about what you're allowed to do with limits. So we know we can separate a big fraction into the limit of the numerator and then the limit of the denominator and then divide them, as long as the denominator is not equal to 0. And it would be equal to 0 in this case, so that's not going to help us. If we could do some sort of factoring and canceling, that would work out, but it's not easy to see how that would happen here. So maybe we'd have to do something with logs, right? Because the variable is up in the exponent. Something to do with logs might be useful, but we haven't learned if we're allowed to do that or not. So at this moment, doing this by hand is a little out of reach. Right? The best we can do is approximate it. Good.
All right. Well, thank you, Professor.
You're welcome. Okay. Anybody else? Questions on anything?